All right. Anna is continuing with third lecture.
Yes, today we will talk about symplectic, Calabi-Yau problem. So the idea will be work more on symplectic manifold, and the almost complex structure will be not integrable. So let's start with define what are the calibrated almost complex structure. We already saw what are tamed. Here we will have an extra condition. So we give the definition, an almost complex structure, J, on our symplectic manifold. So omega is a symplectic form, is calibrated by omega if we have the two conditions. So this is also, sometimes I will call it also compatible, omega compatible J. If we have J state, we already talked about this condition. Remember that was the condition that omega 1,1 is positive, plus the condition that omega is of type 1,1 with respect to J. And we have this condition, omega Jx, Jy is equal to omega xy for any x and y. Okay, when we have this condition, so when we have omega J with J calibrated, this is in literature what is called almost scalar structure. Okay, and as we already did, in a natural way, we can define a metric associated to this structure. So we have a metric G, which is induced essentially by omega and J, and by the convention that we use, let's write the expression, we have that G x y is just omega and then x j y. This is just a sort of convention. Okay, and that's J and median in the sense that we saw in the first lecture. Of course, when J is integrable, so when nj is 0, we have just a killer case, and we will consider the case when nj is not 0. Okay. Before to state the symplectic Calabi-Yau theorem, let's go back to the Kähler case. So we will formulate the Calabi-Yau theorem in terms of symplectic geometry. So when we have a Kähler structure, if omega j is a Kähler structure, then one can define this. Let's call it C omega. That's the set of two forms belonging to the Dram class of omega, for which omega is compatible with J. So we have the previous two conditions, and omega is positive. Okay, the set of these is what is called in the literature the Kähler cone. So the set, if omega varies, then you get the Kähler cone, and by using the DDC lemma that I already formulate, or the bar lemma, is the same thing. One can write the same thing like this thing. We can write in this way, like the set of omega, okay, the difference between omega and omega small in exact form, but it's also DC closed. So we can write in this form, omega plus DDC U, and we impose that omega is positive, okay, in this way, where U is just C infinity function. So it's another way to formulate the same property. Okay, And what we have that the Ricci tensor, okay, is J invariant in the killer case. Okay, and this allows to define in an easy way what is the Ricci form and so on. Okay, let's formulate the Calabi-Yau theorem. First version, the general version, then we will see how to get the second version. Okay, so we consider the Ricci form, as I say. So I will denote by rho, x and y. This is the Ricci form of the Length-Schifter connection in this case. And we have the Ricci, Jx, y for the convention that we are using. And what happened that this is closed in the Keller case, 0 is 0. And if you take the class, the RAM class, represented by rho, this represents up to a factor 2 pi that we can forget. In somewhere I will forget about this factor. Anyways, representing the first chain class, C1 of MJ, of course. This is depending on the complex structure. Okay, let's go to formulate the theorem that solves the Calabi conjecture was shown by Yau in 78. And the formulation is the following. So we have, let's start with a Keller compact, Keller manifold, and let's rotate them just close one form, which represent the first chain class. So such that if we take the class, the Durand class of rho tilde, this is 2 pi, the first chain class. Okay, I will denote just this by C1 to simplify the things. Then what Yau showed is there exists a unique Keller form, which is in the class, let's call omega tilde, which is in the class C omega, okay, that I defined before, so an element of the Keller cone, such that rho tilde is the Ricci form of the new Keller structure. Okay. So what we are saying here that any representative of, let's say, the first chain class, okay, can be written as the Ricci form of a Keller form, which is in the same class. This is what we are saying. And there was a great interest to extend. So the idea is to extend the Calabi-Yau theorem in non-Keller setting. And there are many extensions. Today we will see one, but Friday we will see another one, which is a little bit different. Today what we will do is an extension when you keep all the property for the symplectic form and you weak the condition for J to be integral. Okay, let's try to formulate a little bit the things in terms of symplectic geometry. To do that, we will write a little bit, let's use local coordinate. So let's do this remark. Okay, locally, we can write our omega like sum over alpha beta, G alpha beta bar, and then I d zeta alpha wedge d zeta bar. Locally, we have this expression. And then if we look locally, the expression of the Ricci form associated to omega, this is minus 1 over pi by the convention, second derivative of log of determinant of our metric, P Q bar, or second derivative with respect to this zeta alpha, the zeta bar beta, and then we have this. Okay, this is exactly the expression of the Ricci form locally in terms of the expression of and what is nice that this is local expression, but it's defined globally. A close 1-1 form. This is the nice thing of this expression, which represent the first chain class as we know. Okay, so if we write down rho tilde as the Ricci form of omega tilde, okay, or the new, let's say, killer form, what happens that rho tilde is just rho minus 1/2 pi or ddc, okay, or what? Or the function here is just a notation that we write down, of course, omega tilde n. If you take the wedge product, omega tilde n with omega n, the factor, okay, of omega n to get omega tilde n is just a positive function. And what you do is this notation, log of this function. This is what I mean. That's all globally. Okay. So that's how essentially now formulate the problem. So you reduce the problem, Calabi-Yau problem, you formulate in terms of a function which solve a complex Monge-Ampère equation that I will write explicitly, and this way, okay? So we fix beta, okay, which is our Gibbs homology type 1, killer class. Okay, and omega is just a killer form in the class beta. Then we fix eta in C1 or our manifold. Okay, and what happened that by the DC lemma, the rho, as you can write rho as d eta plus ddc h. Okay, now what you can do is to set up, let's say, we are looking for omega u, by definition, where it is of the form omega ddc u or h, whatever, which belong to the class, okay, such that essentially rho, the Ricci form associated to, let's say, omega u is equal to eta. That's how you formulate the problem. And what we can remark is that rho, the Ricci form associated to, let's say, omega u is equal to rho omega minus ddc, that's the computation log of the function that I mentioned before, omega plus ddc u n power wedge omega n. Okay, so to impose, let's say that omega u, the Ricci form is eta, becomes equivalent to say that ddc of, let's say, our function u minus h, sorry, that was h, log omega plus ddc u n over omega n is 0. That's the equation that you get. So the problem is exactly equivalent to omega plus ddc u power n. You see that you formulate the problem in terms of volume. equal to H plus a constant omega tilde omega n. Sorry, this is omega n. Okay, because the function here is pluri-harmonic, the function that you get here, the DDC closed, so is equal to a constant. And this is exactly the constant that appears here, the C. Okay, and then we just normalize the stuff, normalize H in such a way that the integral over m of E, the exponential of H, omega n, is equal to the integral of omega n. Okay, so this is just the volume. So one can formulate the Calabi-Yau problem internally in terms of the volume form. And this is what exactly one can do. And that's exactly the formulation that we will use to generalize this in almost scalar case. Okay, so if you normalize that, you get C equal to 0. So you can forget that, and that's exactly the complex Monge-Ampere equation that you get. Okay, so now we will write this Calabi-Yau theorem using this tricky, using the volume form, then a normalized volume form, because we checked that is equivalent. So this is the same theorem for Yau, but the symplectic version. This is what we will use. Okay, so we start with our compact Kähler manifold, and this time we saw that is equivalent. Let's say sigma volume 4, which is normalized as before. This gives you the unicity, okay, such that the integral over m of omega n is exactly the volume associated to the new sigma. Then, by Yau theorem, there exists a unique Kähler form omega tilde with the property, as we saw, that omega tilde is in the same rank class of omega, and such that the volume is the same. That is the equation that we wrote before. Omega tilde n is equal to sigma. Okay, that's what is usually called the Calabi-Yau equation. We just write down in terms of volume. And this is equivalent to this system, essentially, that I call star. So how we can write that? Omega tilde minus omega, since they are in the same class, is the difference is an exact form. So let's call d alpha. So we have omega plus d alpha n is equal to our, let's say, sigma, but sigma is a multiple by a function, positive function of omega n. So we will write sigma as E F omega n. And of course, we need the compatibility. So omega tilde has to be of type 1,1 with respect to J. So we have that d alpha is of type 1,1. So J d alpha is equal to d alpha. Okay, so this equation, the equation, let's say omega plus ddcu omega n using ddc lemma is exactly our complex Monge-Ampere equation. Okay, and how I just gave one few things about how Yau found the solution. He used the continuity method that means that essentially he replies, the idea is that he replies F with, let's say, F plus a constant here, which is a constant depending on T. Okay, that's mean that you are taking, in fact, a family of PDE equation, okay, depending on T, and T is in the closed interval 0, 1. And then the idea is to show that the set of T for which you have a solution is open and closed in the interval 0, 1, okay? And then it shows that essentially this is standard technique. We will apply also in other case. So the openness follow from essentially implicit function theorem, and the closure, that's the more difficult part. You need some priori estimate. Okay, so that means a priori estimate it means that you need an estimate for the size of solution or its derivative. So you have to control the solution and the derivative of your PDE. Okay, so let's go to the symplectic Calabi version. Okay, the formulation is similar, so it's just the same version in almost scalar. So everything is the same. We only have J is not integrable anymore. Okay, so we start with J omega G compact almost scalar manifold. This case we take sigma again a volume form. We have a sigma, the form like that is a multiple of positive function of omega n. Then we have the normalizing condition like before. Okay, then what we have, the Calabi, we can formulate the Calabi-Yau equation. I write again, all the equations are the same as before. So this is just a volume. We impose that omega plus d alpha is the same volume. D alpha is J invariant, type 1. And then if we want, let's call this star, if we want that the solution is unique, so essentially alpha unique, because the alpha we'll see later for n equal to 2, that's a property shown by Donaldson, is unique if there exists, but to have also the unicity for alpha, we need to impose the extra condition, this star alpha. What happened for our equation? For n equal to 2, so in real dimension 4, our equation is elliptic. And the solutions are unique. I will show you the proof. This was shown by Donaldson. This is very geometric proof, not analytic proof. And if n is bigger than 2, this is more tricky, it's more complicated because the system is, that's a system, of course, if you put all the equation, is over determined. So let's say that the more interesting case is n equal to 2, okay? For n equal to 2, of course, the system is not over determined. Okay, so the problem that we will see now is for which almost scalar manifold, compact almost scalar manifold, we have a solution for this problem. And before to see existence of solution, let's see the Donaldson proof of unicity. Okay, so uniqueness. of solution by Donaldson. For n equal to 2. We really use geometry in 4-dimensional, and the proof is the following. Okay, suppose we have 2 solutions, so let omega 1 and omega 2 solutions of the symplectic Calabi-Yau problem. Okay, W star, let's say. Okay, what we have is the following. Let's write the condition that we have. So we have that omega 1 and omega 2 induce the same volume. So omega 1 square is equal to omega 2 square in the wedge sense. And omega 2 and omega 1 are the same class of omega, the RAM. So the difference will be, again, a close to 4. Exact to 4, sorry, that I will denote by the alpha. Okay, so if we just, this is just a computation, if we write the expression omega 2, so if you put omega 1 plus this alpha wedge square equal to omega 1 square, omega 1 square goes away, and you just get the alpha wedge 2 times, plus 2 times, because we have 2 forms, okay, 2 omega 1 wedge the alpha equal to 0. Good. Now the trick is the following. Let's take omega 1 plus omega 2. Okay, and let's call this omega tilde, which is omega 1 plus omega 2. And let's look at the property of omega tilde. What we have is omega tilde is still symplectic 4. Non-degenerate, close, and Taiwan 1. This is not a problem, okay? With respect to J, okay? Note that if you work with respect to omega tilde and you take the primitive, okay? The primitive with respect to omega tilde, usually you denote with this. These are just the form, real form, 1 form, primitive with respect to omega tilde. In dimension 4, real dimension 4, this corresponds to the cell dual forms. Okay, so the form for which star odd of the form is still the same form. Okay, if we write down the condition, the previous condition in terms of omega tilde, what we have that omega tilde wedge d alpha, this is equal to omega 1 plus omega 2, which is omega 1 plus d alpha. Okay, so what we get exactly 2 omega 1 wedge d alpha. Okay, and if we do that, the alpha, we get exactly that this is 0, okay, by the previous condition. So d alpha is primitive, okay, and that means that d alpha is cell dual with respect to the metric induced by omega tilde and j, okay. I just denote by g omega tilde. That means the star Hodge the alpha is equal to the alpha, where star is the Hodge to the metric that I denoted before, and then it's an easy exercise. You just apply Stokes theorem. By Stokes theorem, if you integrate the norm square of the alpha, here you just say the volume, the omega tilde, this is just the alpha wedge star of the alpha, okay, which is the alpha wedge, the alpha, this is exact, okay? So by just integrate, you get that the alpha is 0. So we have our unicity. In fact, this symplectic Calabi-Yau problem is connected to other conjecture by Donaldson, were introduced by paper by Donaldson. And we have another conjecture related that is more related, we'll see, to the taming condition. So let's start with 4 manifold and 4 omega j sigma, a compact symplectic for manifold with an almost complete structure J. And impose that is only tamed by omega, okay? And let's take a normalized in the sense that I wrote before, volume 4, sigma. What is the conjecture that if there is omega tilde in the class of omega, okay, the same class, so the difference is again in that form, which is calibrated, symplectic form, calibrated by J, and solving the, let's say, the symplectic Calabi-Yau, problem equation, okay, omega tilde wedge square, the volume is equal to sigma, then there exists a infinity a priori bounds on omega tilde, depending only on the data, okay, omega, j, and sigma. Okay, what does it mean? It means that if you take any k, 0, 1, 2, and so on, then there is a constant, a k, depending smoothly on the data, on omega, j, and sigma, such that you have a control, okay, of the norm of omega tilde with respect to the original metric in terms of this constant. So the norm of omega tilde is less than equal than a k. That means these things, priori bound, depending on that. Okay. This conjecture has nice application if it's true. There is a nice paper by Tosatti and by Cove where they consider this conjecture and they formulate the conjecture, we'll see later, in terms of the Chern connection. Instead of working with the usual Calabi-Yau theorem, you work with the Ricci form of the Levi-Civita connection. But here in the context of symplectic Calabi-Yau, if one wants, one could formulate the stuff in terms of the Ricci form of the Chern connection. We'll see how is defined the Chern connection. It's similar definition that we saw for the integral case, is similar. So some application, let's say, if that conjecture is true, then the symplectic Calabi-Yau theorem holds in particular for compact almost scalar manifold with B plus equal to 1. Okay, here B plus are just, let's say, the dimension of the space of harmonic form, which are self-dual. Okay, that's all you can see as the number of positive eigenvalues on the intersection pairing on the homology. Okay, so is exactly equivalent. That's the first thing. And the second application then, if B plus of our manifold is 1, and there is a symplectic form, okay, then there exists a calibrated form. So omega tilde, symplectic form, calibrated by J. Okay, so this in fact is more general, is related to a more general question by Donaldson. One can forget about B plus equal to 1 and just ask the question, if you have a compact symplectic manifold in dimension 4 and you have this form is same J, then there exists, the question is, there exists a symplectic form calibrated by J? And that's, so the question is the following. Let's say J, almost complex structure on a compact form manifold M, if J is tamed by a symplectic form, omega, okay, is there a symplectic form omega tilde compatible or calibrated, okay, with J? That's a question. Okay, what we can say about this question in general? The first remark, if, of course, one can put this question not only in dimension 4, but in higher dimension, but we will see that it makes sense only in dimension 4. Of course, the first remark that we can say, that if you look at the question locally, the question is true locally, be careful, locally, for all almost complex form manifold. This is not a problem, okay? This is a nice, but is not, now I will say a few words why you work in four-dimensional, but it's not anymore true, even locally, in higher dimension, for n bigger than 2. So there is a big difference about this question in the real dimension 4 and in higher dimension. In dimension 4, there is a nice proof by Rivière and Tian, so the property locally, and there is a new proof in a paper by Leimi. I will quote this later, and this paper is more on nearly Keller case. Okay, why is not anymore true in higher dimension? There are explicit examples. There are explicit examples in higher dimension for which you have almost complex structure that are tamed by a symplectic form, but that cannot be calibrated by any other. The first example was constructed by Adriano Tomassini. And he was on the Iwasawa manifold. So the complex Heisenberg over gamma. So he considered there a almost complex structure, J, there, which is not invariant and is tamed by symplectic form, but cannot be calibrated by any close to form. And then there is this nice paper by Lamy, that's nice, because he showed that in fact, if you take a special almost complex structure, the one associated to an Early Keller manifold. So if you take an Early Keller 6 manifold, okay, so you have seeds, you have an almost Hermitian structure. You can see also in terms of SUV structure, but here I just look that in terms of almost Hermitian structure, you have so a J, almost complex, G is compatible metric, and is characterized by the condition that the Levi-Civita, Levi-Civita x, J, x is 0. Okay, he showed that in that case, such J cannot be calibrated by any symplectic form. So there are examples in 6 dimensions that cannot be calibrated by any symplectic form. And then there is also another thing that one can do. It was done by Luigi Vezzoni, and just showing that if you have in general in any dimension, not 4 dimensions, so n bigger than 2, and you have an almost Hermitian structure for which you have a connection with a compatible Hermitian connection. In this case means that the connection preserves J, so J is parallel with respect to the connection, and also G is parallel with respect to the connection with skew symmetric torsion. You remember the bismuth connection as such property? And Agricola and Friedrich characterize almost Hermitian manifold meeting skew symmetric torsion, Hermitian connection. And if you look in terms of Greyer-Vella classes, it means that you have 4 classes usually who knows the theory about almost Hermitian geometry. And what happened here that the class omega 2 is 0. Okay, so you have only in this class omega 1, omega 3, and omega 4. And what Luigi Vezzoni, that in this case, J cannot be calibrated by any symplectic form. Okay, again. Good. Let's see when the question is confirmed. We saw already a case when it's confirmed. Donaldson question is confirmed. Okay, when? In complex dimension 2, a case where it's confirmed is CP2. So if M is a complex projective plane, CP2, and there are 2 independent proofs. The first one is by Gromov, and the second one by Taubes. Okay. The one by Gromov is using essentially that any symplectic form on CP2 is essentially the standard one. That's also I use in Gromov. And Taubes is using pseudo-holomorphic curves. Holomorphic curves. That means that you have an immersion of your smooth curve in your manifold M, and you have the property that J, the composition of J with the differential commute with J. Essentially, you have this. That's the condition that characterize pseudo-holomorphic curves. And then we have another case, the case when J is integrable, right? And this we already saw, and they were the proof by Sritsentian and Nizam, because asking calibrated tame we saw imply that is scalar, right? So in that case, it's confirmed. And in some Lie algebra, also there are results, 4-dimensional Lie algebra. There are 2 papers by Tian Li with Tomasini. Okay. There is is confirmed, this question is confirmed in the case B plus equal to 1 under an assumption. Okay, that's resulting in a very long paper by Taubes. And the theorem by Taubes is the following. Let's take omega, a compact symplectic form, manifold, so compact symplectic with B plus equal to 1. What it shows, it doesn't show for a generic almost complex structure, but it adds something else, which is generic. I will explain in a moment what that does mean. It shows that the generic omega tamed, let's write like that, almost complex structure. On M is compatible. So it's calibrated. It's compatible with a symplectic form. Omega tilde symplectic form on M. But the nice thing here that it shows something more. Moreover, if you take the class of this omega tilde, the class in omega 2 in I2, sorry, here, okay, the homology, then is equal to the class of omega if omega define a class with in A2 rational class. That's what it shows. Now I will just explain what you mean by generic and give just a naive idea how we show that the result. Use current to prove the result. So generic, by generic, it just means that in an open and dense, let's say subset of, okay, you take the space of almost complex structure taken by omega. This is a infinity Fisher space, okay? So that's what you mean for open and dense with respect to this topology. So subset of this infinity Fisher, let's say space topology in of omega same almost complex structure. How we construct omega tilde, just an idea. I don't, the paper is very long and is also not so easy to follow, but the main idea is to using essential integration using holomorphic curves, because you want to define some currents, right? So you need the duality with 2 forms. So what you do, the idea is to follow the new symplectic form. Omega tilde is constructed by integrating, that's right, like that, over a space of currents that are defined by pseudo holomorphic curves. So again, using pseudo-holomorphic curves. Pseudo-holomorphic curves give many information about the almost complex structure associated to omega. And the idea is the following. So he essentially use currents. He defined what in the literature is called a Taub's current with special property, because this Taub's current is closed positive 1-1 current in the same class. It depends on some constant k anyway, but the important thing that this is the same class as omega, and that's why modifying this current, he obtained a new symplectic form which is in the same class. There is a recent preprint, now is 2 years in the archive by Tan, Wang, Su, who mentioned that, and Peng. It's still a preprint where they claim that they removed the assumption generic. Okay, so they work a little bit more and it's correct, but it's still preprint. So I don't know if it's correct or not. Maybe it's correct. Okay, so let's see now some sufficient condition for the existence of solution, because until now we work only, I mean, on let's say something related to the conjecture, right, to the symplectic Calabi-Yau problem. There is a first result by Weinkopf, where essentially they show that if the Ninoyos tensor is not so big, you have a control in the Ninoyos tensor, then the symplectic Calabi-Yau problem has a solution. It's saying like that. So if you have our compact almost scalar for manifold with B plus 1, then the symplectic Calabi-Yau problem has a solution if the norm of the Ninoyos tensor respect to L1 associated to the matrix G is less than epsilon, okay? For epsilon, depending only on G and the norm C2 of F. C2 is always with respect to the matrix G. And then there is a sufficient condition found by Tosatti, Weinkopf, and Yau, and is in terms of the chain connection. When you have almost scalar, this is in all dimension, almost scalar M2 and J, there exists a unique, so almost scalar, but there still exists a unique connection that is still called the chain connection. Canonical is also called, such that preserve J, preserve the symplectic form, and then the metric, and the one part of the torsion of our connection is 0. Okay, and there is a sufficient condition by Tosatti, Weinkopf, Yau, that ensure that if you have such condition, that you have a solution. This is in all the dimension, and is a sort of, let's say, positive of some curvature, some, let's say, like a sectional curvature, but it's not really the sectional curvature because it's involving also the Ninoyos tensor. But if you have this positive, now I write down the expression, the components of this, which is defined by this. So you have 4 indices, E, J bar, K, L bar, and this is just a chain. And then you have E, K, L bar, J, you see that, plus, and you have a part with involving the Ninoyev tensor. G bar, and then N bar, I, R bar, K bar. Whatever is the expression, you have a sort of, here you are using a unitary frame. And so under this assumption, you have that the symplectic Calabi-Yau problem can be solved, okay, for any normalized, for n equal to 2, 4 dimension. Okay, and they show that in fact you can apply also in higher dimension, for instance, for a deformation of Fubini study and so on. But it's very hard to apply this condition. And so let's go back to the Kodaira-Thurston manifold surfaces that has B plus equal to 2, so it doesn't belong to this family, or B plus equal to 1. What Tosatti Vainkov show that if you formulate the symplectic Calabi-Yau problem for the Kodaira-Thurston manifold, the non-killer surfaces, then you have a solution for a specific omega. We'll see which one, and for a specific almost complex structure. The first part that we can do, that the condition that we wrote before, so the existence, let's say result by Tosatti, Vainkov, Yau, cannot be applied in this case for our Kodaira-Thurston surface. Remember, we saw that in the first lecture. Was an manifold, was a product of this quotient. This is just the real Heisenberg times S1. I don't write anymore the expression of, we just simply write in this way, associate, let's say, structure equation of the Lie algebra that we have. And what is important to remark that we have that this is a total space of, to distinguish, I will denote by T with 2, let's say, in line, the fiber, and I will use T2 for the base. Okay, so it is a T2 bundle over T2, and the way is just the following. Maybe use some color here. Yes, we have S1 here. Then we have this, just to understand, well, here is just a projection over XY of our torus basis here. And then we have the other one, it's called like that, our factor here, just to understand what is going on. Here we are S1. So it's just the projection over the coordinate X and Y. Why is not taking this? Okay, that's, so this is the our fiber. Okay, and our base. Good. And 4, you can consider, for instance, this symplectic form, 1, 4 plus 2, 3, okay? And you just send J1 in 4, J2 in 3. What happened here that is Lagrangian, the symplectic form is Lagrange. That means that it's vanishing on the fiber. And what Tosatti and Vainkov show, Tosatti, Vainkov show is the symplectic Calabi-Yau equation. Calabi-Yau equation on our Ecodyra-Thurston manifold M4 with the previous choice of omega j can be solved with an assumption on the volume form. For every T2 invariant normalized volume form. So it's not for every volume form, but you just like T2 invariant. That's allowed to reduce the problem to something working on the base. Okay, the function depends on the base, on x and y, and so on. In the slides, you can find an idea how it's working. The proof is not so complicated. The main thing is to get a bound for the trace of the new metric with respect to the previous one, and then to apply the continuity method. We in collaboration with Yan Li and Simon Salomon and Luigi Bezzoni, we try to have a different proof of this result, and this allows to generalize this result for any T2 bundle over T2, okay? And with, again, for every T2 invariant normalized volume form. And I want just to write, to give an idea how it came, the stuff. So if you can see the previous Calabi-Yau, symplectic Calabi-Yau problem on the Ecodyra-Thurston, doing this change, you can do this extra change. We don't have, of course, the main problem in almost scalar geometry that you don't have anymore a DVC lemma, okay? There are some results, some tentative to show that, but essentially you don't have. That's the main problem. But the nice thing here that we will reduce the problem to not anymore a complex Monge-Ampere equation, but a real Monge-Ampere equation in this way. Let's start with the Ecodyra-Thurston, okay? Surfaces, manifold, with the omega, that choice of omega. Okay, we want to this is the problem, right? That we want to solve. The volume associated to omega plus the alpha has to be our sigma, okay, with the normalized. The trick is the following. Let's take alpha, not really. If you take DC of something, then you have the alpha is the DC, right? So you go back to the Calabi-Yau case. But the trick here that what we did is the following. Let's take DC V of a function and remove the duration along E1. So minus V E1, okay? And V is just a function on the base. We can reduce that because remember that we have an assumption that the volume form is T2 invariant. So we work essentially is invariant with respect to the action of the fiber. And the trick is that if you compute then the alpha, this is just essentially Vxx E3 plus Vxy in 1 in 3, just a computation. I did again. Okay, that's the computation that we have. And so what is nice that the previous, let's call this equation becomes a real Monge-Ampere equation of this type. 1 plus Vxx, if you do the computation, 1 plus P second derivative yy minus v squared xy equal to EF. That's the equation that you get. So what you get? The determinant of identity plus Hessian equal to EF. You get the type of real Monge-Ampere equation on the torus, on the base torus T2. Probably I denote with one line. I don't remember. Okay, so that's for this case, we can apply a general theorem due to Lee, to Yang Lee. Okay, Yang Lee. So we have, let's write here, determinant of I plus relation. We can write in this way. Okay, x1 is just x, x2 is just y, equal to our positive function. And one can use a general result by Lee, this theorem by Lee, that say that the Monchampère, the real Monchampère equation, is not only on the two torus, but it's on Tn, in general T2n torus, determinant of that equal to EF. Of course, here we have a condition that this is positive, that's positive, and you take the standard torus Tn, and that's as always a solution. Always a solution on the standard torus. Standard torus Tn. Okay, and you have this extra condition that is the integral over Tn of f minus the determinant, or say 0 is 0. Okay, you have this extra condition. Okay, what we did is generalize. That's a paper with generalization. It's a paper with Yang Lee, Salomon, and Bezzoni. We generalize that for T2 bundle over T2. Okay, and for sigma, again, T2 invariant. So invariant. So again, you will work only on the base space. I have no time to give the detail of that are in the slides, but the idea is to use in general the property of T2 bundle over T2, and one of the property of T2 bundle orientable, of course, because is they are geometric in the sense of Thurston. I just so remember that the geometric for manifold is just a pair X and G, where X is a complete simply connected Riemannian for manifold, and G is just group of isometry acting transitively on X that contain a discrete subgroup gamma, such that if you take the quotient X over gamma, this is as finite volume. So what happened by UE result? That if you take every orientable T2 bundle over T2, this is a geometric for manifold. it's just a geometric form manifold, and you have essentially these cases, R4, then the usual isometry, the semi-direct product of R4 with SL4. Then you have our, which correspond to the terson, mean free, cross R, and then you have some part, mean free, which are just a translation, but then you have an extra rotation. So you have something times S1. And then you have the other possible four-dimensional impotent group in 4. Here the isometry is in 4, and then the solvable case. So free, cross R, and here again the isometry is again solve free, cross R. Okay. In all these cases, you have not really a compact but it's called a manifold. So that means that up to a finite quotient is a compact manifold that we saw, and it's nice because essentially they are completely classified. Okay, this T2 bundle over T2, and what we show, that's our result, our theorem, that for any we show this, in fact, at the beginning, I mentioned I should mention 2 papers, because in the first paper that I mentioned with Yan Li and Simon Salomon, Luigi Vezzoni, we consider the Lagrangian case. Okay, so the case when the symplectic form is vanishing along the fiber, and then later with Buzzano and Vezzoni, we realize that the result is also true for non-Lagrangian case. But the nice thing that all the problem reduce to an equation, okay, to an equation that I will not write, but the nice thing that there is a constant in this equation, that's when it's vanishing this constant in the equation, which is a real Monge-Ampère type, then you get the Lagrangian case, and in the other case, the non-Lagrangian case. So that's quite nice as a picture. So this is in 2 papers, Salomon and Vezzoni. That's the Lagrangian case. And then in another paper with Ernesto Buzzano and Vezzoni, we show essentially that if we have a T2 bundle over T2, be careful that here I denote with this quotient, but it's not true in general that gamma is a subgroup of X. If gamma is a subgroup of X, is a discrete subgroup, then you have a solved manifold case. But in general, you have not really. Gamma contain another lattice on X, and the quotient is finite. That's the idea general. We need some hypotheses on the almost scalar. We need an invariant almost scalar structure. That means that is induced by left invariant almost scalar structure on X. X is a group in all the case, which is also gamma invariant. That's what we need. Omega J G. Then for any normalized T2 invariant volume form, sigma, we have a solution. The symplectic Calabi-Yau problem as a solution. And the unique solution, of course, we know by Donaldson that is unique. So the idea is to use the classification of that and to reduce everything to a real Monge-Ampère equation, which is more complicated than the one that we saw before, but the idea is similar. we classify almost scalar structure, and then we reduce this Monge-Ampere equation, and then we apply the continuity method to solve that the Monge-Ampere equation as solution. That's the moral part, the priori estimate. I want to finish in the last few minutes with another result, the last one, where it's with Buzzano and Vezzoni. And we try, okay, the idea will be in the Kodaira-Thurston manifold not to have any assumption for the volume, right? Because we have this assumption on the volume that has to be, the volume has to be T2 invariant. So we try to make weaker this condition and to see the KT manifold, in fact, as a more rich structure, because you can see as a S1 bundle over a free torus. How you see that? You can do something like that. I use again the color maybe. So we have, okay, we have our part, let's say. We have the projection here, T2 XY. And here we have S1 zeta, let's say. Okay, so zeta is the phi, but we correspond to the center. And then here we have S1 T. This is our, for manifold, our Kodaira. And here we have S1 T, which is our T. Okay, the coordinate. That's the thing. And what we did is to show that the symplectic, that's a theorem with Buzzano and Vezzoni. And we show that for any, let's say, for any sigma, we have still these things. So omega, the same, our Kodaira-Thurston, J, omega. Here we can take omega the same like the other one, but it doesn't matter so much, okay? The important thing that here this sigma is just S1 invariant, okay? So that means that the function here is a function on this torus, in fact, T3 X, Y, T. We show again that the symplectic Calabi-Yau problem as a solution. And this time the equation doesn't reduce to any more real Monge-Ampere equation, but another type of equation that is more complicated, is fully nonlinear, PDE. And then later Tosati, Van Kove, you can see from the slides, gave a different proof of that using a result by Seclidi. The more hard part is, of course, the priori estimate, especially the C0 priori estimate. Then they found another way to show that. We have, in fact, a formulation of the problem without this extra assumption as one invariant that reduce anything, just working on this product, right, on our for manifold. And the problem here that the PDE theory on that type of Heisenberg quotient by gamma and is not clear. I mean, there are results for what is called the sublaplacian, okay, which is just involving this part, okay, this part, right? But what we will need, and that's theory that is missing, is some theory involving the extended operator. So the operator that you use with all the coordinates. This we don't know. This we don't know. Is not, there is very few notes about PDE, and it would be nice to have that because we have the equation, but we cannot solve that. We are stuck there. And I think it's a good point to to stop. I was in this last part, I was less technical, but all the details of the proof are in the slides. So if later you have questions, you can just ask me. And I think I will stop here.
Great. Any questions? Very nice results. Thank you very much.